Yes, I'm Tim Edwards. I work for Efabless. My main claims to fame are that I helped a lot on the Sky 130 Open PDK. I did a lot of the analog parts while Tim Ansel was doing the digital parts. Tim Ansel came up with the idea for the Caravelle harness chip, and I architected it. And also, I am the developer and maintainer of some famous EDA tools like Magic, IRSim, NetGen, a number of which have been mentioned, including in the last talk. So, and I'm going to talk today about a new project I'm working on called CACE. That stands for Circuit Automatic Characterization Engine. So here's the history of that, which is that once upon a time, which is about 5 years ago in pre-pandemic days, we had a platform called Open Galaxy at Efabless, which was a set of cloud-based servers, virtual machines that we could give to people, and it had all our tools loaded on it. But we were, at the time, working with a obfuscated process. That was the XFAB XH018 and XH035 processes. And the problem with that was that all the primitive devices were not able to be open source, so we couldn't show those to the users, but we wanted the users to be able to do designs on our system. So we needed a way to for them to verify the circuits that we had on our system. And so we created this system called CASE, which was basically a set of Python scripts. And we used that in what was our first analog design challenge, called, which was to design a band gap in the XFAB XH035 process. And so people used this system, which I'm going to describe in a bit, and they were able to make good analog circuits without ever being able to look at the primitive devices, or so they could only simulate through this system. But that's the first place winner, and I believe that's still up in our marketplace. So what we gave to the people who were the designers was a spec. This is a cleaned up spec in PDF format, but that was basically what we said. These are the parameters that we want you to hit for the band gap. And they went and designed to that using this system, which looked like this on the platform, and I will show you it's pretty much the same now off-platform, but I presented the results of that and how people use the system at the WASH conference in 2019 in Zurich. Now fast forward past the pandemic to now, when we have the SkyWater Sky 130 Open PDK and everybody can work on their own computers, and all of the primitive devices and everything else about the PDK is open source and available. And at the same time, we came up with the Caravelle harness chip for digital design for the first OpenMPW, and then by the time that we did the second OpenMPW, there was clearly a lot of demand for analog circuit design, and so I created the corollary to Caravelle, which is Caravan, which is the analog project harness. There is actually not that much difference between that. It's got the same RISC processor on it, the same user project area. The main thing I did was I ripped out a number of the digital I/O cells on the top and replaced them with analog straight through pads. But after a number of OpenMPW submissions, we found by and large that a lot of project submissions were incomplete and not reproducible. That means we would get GDS from these people, but if you went to their website, it was supposed to be open source, but where are the design files? They're not there. And we could only require them to do GDS because we didn't have any flow to do automatic checking of LVS or other things. So we basically told them, oh, it's okay just to produce just to produce GDS and give it to us. But that means they took advantage of it to break the general principle of the OpenMPW, and so you end up with broken things. Also, the circuits themselves were broken. There were a lot of mistakes in these designs. People were missing very essential things like connecting up their power supplies. Not for every single one, but there were some, yes. And the community was just by and large unfamiliar with the open source tools. So what we really needed was a structure around the analog design to ensure that we could have reusable analog design. And the general principle here is that if you have an open PDK and you have a design in a public Git repository, then you should be able to completely verify that. You should be able to download that and say, I can prove that that circuit behaves exactly as the designer said it did. And so this is a long-term project. It's a long time in coming, but I had intended for a long time to do this, but to import CACE from the platform to GitHub. And as somebody earlier today mentioned, you have to put up your page with the GitHub, show it's there. That's it, github.com/efabless/CACE. So now it is open source and downloadable. And thanks to Leo Moser, I have a installation for this that is on pip. So since it's a bunch of Python scripts, all you need to do is do a pip3 install CACE, and you've got it. So what is CACE exactly? Well, I did not intend it to be a design tool. I intended it for verification. It could potentially be used as a design tool. If I wanted to describe it, I'd say it's a tool for allowing analog and mixed signal circuits to be fully characterized across corners and with Monte Carlo and mismatch analysis using open source tools in a way that is formalized enough to allow any circuit pulled from a public repository to be both verified and reused. So the root of this is a specification file that describes your circuit and specifies the circuit. And that has to have things like metadata, dependencies, file system paths, circuit pins, electrical parameters. That's the main part of it, the electrical parameters. Physical parameters, which are parameters based largely around the actual area of the chip and the physical verification. Then there are default conditions that describe what the conditions are when you don't say otherwise. And then for each of those electrical parameters, you have to have conditions for each of the parameter measurements. And then a section that describes what simulation tool you use, how you do the simulation, and how you collect the data, how you make the measurements. And then there's a section on how to do plots. So forgive me for making yet another file format here, but I wanted something that was easily readable and easily editable in Vim, and so I came up with this. It has, for instance, up there's the metadata. You have things like the circuit name and description and your license and your own information, such as your own name and company. File system paths. I didn't want to be too restrictive about the paths, but I do need to enforce some kind of file hierarchy on people so that the tools can figure out where everything is. For the circuit pins, this is your standard pinout as you would find in a data sheet. It's got your pin names, descriptions, types, whether it's input, output, or digital or analog signal, power, ground. Here's your default conditions, which is something you usually find on data sheets. If the electrical parameter isn't otherwise specified, these are what the conditions are. And then each of the electrical parameters has its own section over on the other side. Spec limit says, for this electrical parameter, here's the minimum, maximum. If I want to have the tool tell me that if I'm out of limits, I fail, and I can just type fail there, and it will alert me. Tells me that I want to simulate here using ngspice, and what the output's going to be. In the best case, I can have ngspice do the measurement, and it just spits out the value of the electrical parameter, and it simply goes and calculates which is the minimum or maximum. Otherwise, if I'm using Zeiss or something that doesn't have all those measurement capabilities, I will just dump a bunch of data and feed it to another tool, and then I'll have another section there called measurement, which tells how to read all that data, and it will pass it to another program, which might be Octave or Python, to do more processing, and it will dump the value of the electrical parameter. And then, of course, conditions, so I can measure over common mode voltage or temperature, corner, so forth, and the CACE is responsible for figuring all that out. So here are the things that CACE requires from the designer, that your file system structure needs to be at least somewhat regular. And that means you need to have cleanly separated circuit schematic, circuit symbol, your test benches, all those need to be cleanly separated. You need to have a test bench for each of the measured parameters, although you can reuse a test bench for different parameters. And you need that file, which is the complete specification of the circuit in a human-readable format. And then all the design files need to be in a single repository, or else if you are reusing parts of your circuit from another public repository, you need to declare those, and the tool needs to be able to find them and download them. So if you have done that much, then CACE itself does the following, which is enough things that it covers 2 pages here. So it manages those dependencies. So if it sees a circuit that you're using that's a public repository, it will go clone it and manage it. It will do schematic capture of the circuit. It will do schematic capture of the test benches. It will extract the layout with and without parasitics. It can check the schematic for whether the devices are valid for the process that you have declared it's going to be for, and it can estimate layout area from the schematic. Furthermore, it can substitute the net lists, depending on which net list you wanted to, schematic or simulation post layout, substitute that into the test bench, determine the set of conditions requiring simulation, so how many corners, how many temperatures, how many voltages, and how many total unique conditions does that mean, and figure out how many simulations it has to run. Then it will do the simulations. It will run them multi-threaded across all of the conditions. And as I mentioned, it can post-process the data either within the simulator or, depending on what you want, Octave, Python, or otherwise. If you have given it a Monte Carlo process, it can figure that out and will run statistical analysis and give you mean and standard deviation. It will compare the measurement results that it gets for each of the electrical parameters against your spec limits and tell you where you have passed and failed. And it will generate plots over various selected vectors that you tell it. And finally, you can press a button and it will give you a nice datasheet in HTML format for the whole thing. So here are a few examples. This is what it looks like when it runs. It gives you a big GUI with all the some metadata at the top. Electrical parameters are in rows going down. Some of them may be describing plots. Some of them may be describing physical parameters. And then in columns, you've got your circuit specification listed as minimum, typical, maximum. So this is presented in the form of what you would normally see in a data sheet for a circuit. So looking at some of these things, like I have a parameter that is offset error, and it is related to a test bench, which is called input offset.spice, which comes from a test bench schematic. And the test bench schematic looks like this. What I mean by cleanly separating the symbol and schematic and test bench is that the symbol here is completely separate from, or it is instantiated within the test bench, but is separate from it. And in the test bench, you should only have test bench components and any setup that you need for the simulator. So looking at the simulation setup and the control block, the heart of this thing is that within your test bench, you have variables. So I'm effectively extending the syntax of ngspice here by allowing things like my include file to be a variable that CACE knows about. So when it wants to find the schematic netlist or the layout netlist, it will substitute the right one into there. You can substitute in the temperature and the corner. So all of these things are coming from what is described in that characterization file. Likewise, if you need equations, for instance, I have added equations to ngspice where it otherwise can't do them, such as I want to measure where the output signal crosses 1/2 VDD. So I just put in VDD over 2, and whether I'm simulating at VDD or VDD plus or minus 10%, it will calculate out the half value. And the components themselves can have the variables as part of them, so that in this case I'm constructing a PWL signal for my voltage source, and the PWL signal is a triangle wave going up and down, and the rise time of that is a variable that is being picked up from the simulation file. And also some of my variables can be binary, and if you want a binary value, like in this case enable is a binary signal, 1 or 0, and it'll just multiply that by the digital power supply so that it gets the right value for the voltage source. So once you have hit the simulate all button up at the top, then it will run through all of the simulations and provide an output that lists you all of the specs in the left column and the actual results in the right column. And if in that place where it says pass on the status, each one of those is a button, and if you click on that, then you get a tabulated view of all the results. The tabulated view itself has buttons at the top, so if I have, say, temperature as a variable, and I click on that, then it will turn that into a graph, and I can see what is the result over temperature for different corners and different common mode voltages. And when I press that HTML button, I get this result, which is in HTML, so I can pop that up on GitHub along with my circuit, and anybody can see at a glance exactly what the results are. And here's another example that comes from an 8-bit RDAC, and showing that if I have a parameter that is a Monte Carlo simulation, that all I need to do is in the characterization file simply say I want to run this over a number of iterations, and CACE will pick up on that, and if I click on the button where it said fail there, it will print me out a nice histogram of the results. In this case, there are 2 results, and it's clearly going a bit out of bounds as you get up toward the top range of the DAC. And if I want to change from my schematic simulations to RC extracted, I just go up to the top corner, select the button, select RC extracted. Now, CACE isn't going to help me make the layout, but assuming that I have a layout and CACE knows where to find it, then it will use that to make the netlist from the layout and insert that into the quote .dot path, and I will get a simulation over the layout netlist instead of the schematic netlist. It's as simple as that. So I put this into practice just a month ago for the Chipalooza 2024 challenge, which is sort of a reboot of our original challenge, except for Sky 130. So we wanted analog blocks. We wanted an analog library. And so we wrote out specifications for 21 different analog blocks. And when we held the challenge, we got back over 40 proposals. And of those, 15 designs were ready for layout in under 40 days, and although the tape out has not come yet, and I only have a few days left for it, it looks like about 10 designs will be ready for that April shuttle run. Now, designers were not forced to use CACE, but they were strongly encouraged to use CACE, and while correlation does not equal causation, it is helpful to note that of the 15 designs that were ready for layout, 12 of them were using CACE. And then of the 9 designs that we managed to get through schematic review but didn't make it to tape out, 1 of them used CACE. So for future development directions, mostly just minor bug fixes. I don't think there are any particular major things to do here, but better handling of search paths at xschem, having, depending on how you end up working with xschem, it makes it easy to break. There should be support for different tools. I'm interested in the Cedar EDA that was presented yesterday and trying to see if I can get that to work in CACE as well. More complete handling of the dependencies, which is another place that's easy to break it right now. More efficient simulation handling, so it doesn't have to do redundant simulations as it's often doing right now. And there are some mixed signal simulation options that used to be on the platform based on some obscure branch of ngspice that have been now put into the main development branch or main distribution branch of ngspice 42. So it's time to go figure out how to update that to ngspice 42 and get them working again. So my conclusions are that CACE fosters trust in open source analog design. It encourages good analog design practices. It simplifies the process of complete characterization, and it makes design reuse easier. And that is all I have to say about CASE right now, although I'm hoping to do a workshop tomorrow that, if properly scheduled, is going to happen after the one on the TL Verilog with Steve Huber. So, and finally, I have one surprise for everybody, which is that if you capture that QR code, we are raffling a tiny tape out. So somebody will get to win a $300 worth tiny tape out slot, and you can do whatever you want with it, although tiny tape out now does support analog. You're free to do digital, because I know a lot of you are digital designers. Sorry, oh, you're giving out 10 of them? Oh, I am sorry. It's 10 times better than I thought. We are giving out 10 of these. All right, thank you.
If anyone has any problems signing up, just shout out and let me know, hopefully. Tim, looks really good. Thank you. I'm not an analog designer, but I've looked over the shoulder of enough analog designers to get a feel for what Virtuoso is. Is this basically open source Virtuoso?
I am sure. I have not actually used this kind of a system on proprietary tools. When I used proprietary tools, I was mostly doing just the analog circuit design, so or the analog layout more than anything else.
Yeah. Yeah.
Yeah, I'm assuming that the commercial tools have things like this. I'm not familiar with them and don't know how to use them.
You're probably lucky, actually.
Yeah, that allows me to come up with this from scratch. That's the way I work. That's how I don't get sued by the proprietary tool vendors, is that I just ignore what they're doing and come up with everything by myself.
Very good. Good strategy. Questions? There must be some. Yeah, Kurt.
Is MPW most of the business, or is there a lot of people buying full wafers?
Well, MPW was funded by Google until Google stopped funding them at the end of MPW 9. So other than a couple of GF process ones that they did after that, there are no more open MPWs until we can get somebody to underwrite an entire wafer.
Our product typically is sold to product companies. That's our name. The MPW is always going to be a project specific. It's not our business model using chip ignite and then go to production.
Yeah, chip ignite, and then chip ignite is the product, and then to production. Ethan.
Fantastic. Is CASE primarily for like tiny tape out and Caravel, or can it be used for like any sort of like VLSI project?
It can be used for anything. Yeah, it's meant to be quite generic. If you've got a analog circuit, as long as you can write the specification for it, and I've tried to make the specification easy to understand and easy to copy and edit. Use of it depends on what's up in the GitHub. If you have lots of examples, then it's really easy to adapt to something new, and that's one of the reasons for doing this challenge, the Chipalooza challenge thing, was to get some of that stuff up there, start getting the examples up so that people can start using them.
That feature to stream out all the results as a HTML page, that is revolutionary. I've seen like the results of analog sims just screenshotted and put on like a page. Yeah, I don't think there's an easy way to get that stuff out of Virtuoso, like in a machine readable, writable format.
Yeah. The funny thing is I wrote that part in about a few hours.
Yeah. Hey, let's not go there. All right, but I think we have to wrap it up. Thanks, Tim. Fantastic work. Cheers.